This is the second video in the series for reinforced concrete, and it deals with partial factor method. This video explains within the ultimate limit state design how to use the partial factor method for the loads. If you look at the design value of a load, that means the load that you use in your calculations, then the design value equals a partial safety factor times a characteristic value of the load. If you look at the materials, the design value for a material is the characteristic load divided by a partial safety factor. If it's about steel, then it's gamma C instead of gamma M. If it's about concrete, then it's gamma C instead of gamma M. The partial safety factor, the content of a partial safety factor can be described as follows. It will be always a combination of the uncertainty of properties and the uncertainty of modeling. I'll give you an example. Uncertainty in the representative values of loads is given by gamma F, but for instance, just the proper weight of soil. Is it 17, 16, 18? It depends on the humidity of the soil. You can have a model uncertainty in the actions. For instance, is it fixed or simply supported? And those two together give you the partial safety factor on the loads, gamma F. On the other hand, you can have model uncertainty in structural resistance. For instance, the stress strain diagram, it is parabolic rectangular. So it's an approximation, so you have an uncertainty. You can have an uncertainty of material properties, for instance, like the yield stress. So those two combined give you the uncertainty on the coefficient for the materials. So this is important to understand that the safety factor is in fact always a combination of an uncertainty of properties and an uncertainty of modeling. Let's take an example. An example for the material factor of concrete in consequence class 2. In general, we have seen that the material factor is a combination of uncertainty on properties and uncertainty on modeling. The gamma RD can be split up in two elements, D1 and D2, and the other gamma M is equal to the characteristic value of the resistance divided by the design value of the resistance. The characteristic value is always the mean minus K times the standard deviation, but the standard deviation can be expressed as a percentage of the mean, and the K value is chosen for the kind of limit that you take into consideration. So here we take for the 95% exceedance. So the K value will be 1.64. And the RD, the resistance, is the same thing, unless on the standard deviation, we have to multiply with the reliability index beta. So for the model, gamma RD is 1.05, and the geometry gamma RD2 is also 1.05. For a characteristic value, you arrive at K equals 1.64. The standard deviation can be expressed as a percentage of the mean, so the delta R is 0.15, that is seen on site. The sensitivity factor, it's the standard deviation of the resistance divided by the standard deviation of Z, and Z is the resistance minus solicitation. So the sensitivity factor is 0.8, and the reliability index, it's the mean divided by the standard deviation of the variable Z, it's 3.8. So we've seen that in lesson 1. Now, if you fill this in this general formula, you arrive at 1.52, so we round it off to 1.5. So that's where the material factor of concrete is coming from this reasoning. Give you another example for the material factor of the steel or the rebars at consequence class 2. This stays always the same, it's the same principle. For steel, gamma RD1 is 1.025, and for the geometry, it's the same as for the concrete, 1.05. Characteristic value, it stays the same at 1.64. Standard deviation as a percentage of the mean, we can see by test that this is only 0.05. The sensitivity factor is the same, it's 0.8, and the reliability index is also the same as with concrete, it's 3.8. So if we do the math, then we see that we can round it off to 1.15, which is the partial safety factor for steel. If you now make a graph, and on the x-axis you put the force, and on the y-axis you put the resistance. Now, if you look at the force is in fact a probability variable. It's a variable with a certain probability and a probability distribution with a mean and standard deviation. And if you take the 95% exceedance value, then you have the definition of the characteristic value of this load. If you start from this characteristic value and you multiply with the safety factor, you have the design value of your force. So this is important to understand this. The load, in fact, is not one particular figure. The load is a probability. It's a probability distribution. And you have a mean and a standard deviation. We take the 95% exceedance, multiply it by the safety coefficient, and we have the design value. And this design value we will compare with the resistance of the structure. Is the same thing, that in the resistance of the structure you will have a 95% lower limit, and then you divide by a material factor and you compare those two. So this is exceedance, 95% is smaller than all the other data, and on the other hand we have the undershoot, which is 95% is larger. Now we will look at the partial safety factors for loads in more detail. You have a load F. From the load F, you derive a characteristic value by means of probability distributions. You divide or multiply, because it's a load, sorry, you multiply it by a safety factor and you arrive at the design value. The characteristic value is the mean plus 1.64 times the standard deviation, because it's the 95 exceedance limit. Of course, if this is favorable, it can also happen that you should take the minus sign for the unfavorable combination. And then the design value is just multiplying the characteristic value with the safety factor. The characteristic load, if you have to do probability studies every time you want to study a building, that will be a very lengthy business to do. So luckily for us, the characteristic value of the load is given in NBN EN 1991. So in Eurocode 1, all the characteristic values are given. Bear in mind that if you have a load which is not in Eurocode 1, listed as a characteristic value, bear in mind that you must convert it yourself to a characteristic value. Don't take just the nominal value, because then you are not well, then it's not very good. A permanent action. We are going to give now some definitions to be sure that we talk the same language. A permanent action, that is an action that is likely to act throughout a given reference period and for which the variation in magnitude with time is negligible, and or for which the variation is always in the same direction until the action attains a certain limit value. So it is connected to a reference period and to a variation in time. A permanent value is limited, small variation compared to the given reference period. A variable action is an action for which the variation in magnitude with time is neither negligible nor monotonic, compared with the given reference period, of course. An accidental action is an actual action, usually of short duration, but of significant magnitude, that is unlikely to occur on a given structure during the design working life. And then we have definitions like a combination value of a variable action. The combination value is a psi0 times your action. Its value chosen insofar as it can be fixed on a statistical basis, so that the probability that the effects caused by the combination will be exceeded is approximately the same as by the characteristic value of an individual action. A combination value is nothing more and nothing less than taking into consideration that two variable actions can happen on the same time, at the same time. But they will not act for 100% of their value on the same time, because the probability that this will happen is lower than the probability that the first action will happen, plus the probability that the second action will happen. So that's why we have combination values. The frequent value, it's a value determined insofar as it can be fixed on statistical basis, so that either the local time, the total time within the reference period during which it is exceeded is only a small given part of the reference period, or the frequency of it being exceeded is limited to a given value. And we are talking here about a reference period of weekly. So that's the frequent value of a variable action. And then you have quasi-permanent value of a variable action. It's a value determined so that the total period of time for which it will be exceeded is a large fraction of the reference period. So we must think a little bit about that. You have a variable action, but each variable action is not the same. Some variable actions, they sometimes occur, they occur almost every time, almost every day they will be there. So now we treat it also differently, and that's why we are talking about a frequent value on a weekly basis. The value is there, let's say, every week. And a quasi-permanent value, it means it's almost always there. So that's why there are two different values, psi1 and psi2. Now consider the limit state. We have on the one hand the ultimate limit state, which is in short ULS. There are three ULS limit states. The fundamental combination or the persistent combination is ULSP. You have the transient combination ULST, and you have the accidental combination ULSA. Next to that, you have the serviceability limit state, which is the short of SLS. Characteristic combination is SLSK, the frequent one SLSF, and the quasi-permanent one is the SLSQ combination. The ULS is there for stability and collapse, to avoid collapse, and the serviceability, that's for the use of the structure. Of course, there are other limit states like fatigue and seisme, which is not ULS nor SLS, it's a category separate. But we will not deal with those limit states in this course. Now look at the ultimate limit state and in the fundamental combination. The plus means that it means to combine with. This is the permanent loads times their combination factors. It's all the permanent loads. You add them up and you combine them with the pre-stress. This is PK is the pre-stress. And then you take one mobile load, the main mobile load, multiply it by its coefficient, and combine it with all the other loads with the combination value. Remember, all the variable loads, the probability that they will happen at the same time for 100% is not happening. So you have to multiply them, apply them with the psi-null factor, which is the combination value. So this is an equation, and you have to take every time another mobile load as a first mobile load and combine it with the other mobile loads. So if there are three mobile loads, this equation represents three equations, in fact. The transient combination is exactly the same, there's no difference. In the accidental combination, then you will see that the permanent loads, you have to add them up, the pre-stress, then you take one accidental load and combine it with the C1 value of the first mobile load, which is not an accidental load, and then you combine it with all the others with the C2 factor. For the serviceability limit state, you have the characteristic combination, which means you add up all the permanent loads, you add the pre-stress, you take one variable load and combine it with the psi-null, psi-zero factor times all the other permanent loads. The frequent combination, which is logic, you will combine it with the psi1 factor. Yeah? You remember the psi1 Q is a frequent combination. It happens weekly. And you combine it with the psi2 combination of all the other mobile loads. And then the quasi-permanent combination, SLSQ, there you combine the permanent loads with the psi2 combination of all the other variable loads. The ponderation coefficients, the gamma I for ULS persistent and temporally, and the ULS accidental and the SLS. You will see that for the permanent loads, you have 1.35 for ULS and ULS A1. Then the gamma Q for the ponderation coefficient for the mobile loads is 1.5 in ULS A1, and the pre-stressing is the coefficient is 1. In SLS, all coefficients are also 1. These are the ponderation coefficients of the loads. Now we talk about the psi factors, psi0, psi1, and psi2. All actions are divided in different categories. And according to the category, you will have a different psi factor. For instance, for category A, which is domestic, the most common category, the combination value is 0.7 times, and psi1, the frequent value 0.5, and the quasi-permanent value 0.3. So 0.7, 0.5, 0.3. Remarkable is if you look at snow loads, the C1 and C2 factor are 0. So you don't have to combine them. It means that the snow load must not be combined together with the other loads. But don't make a mistake. If the snow load is the first variable load, then you combine it with the C1 and C2 factor of the other loads. But you never take a combination of C1 and C2 of the snow load together with an other primary action which is not a snow load. That's the first remarkable thing, but something else happens too. If you calculate a crack width, for instance, for a flat roof, then you don't take snow into account, because for a crack width, you calculate it in SLSQ, SLS quasi-permanent, and there the C2 factor is 0 for snow. So it's a little bit tricky to think about that. So what we will remember, and you should know it by heart, because it makes it easy when you calculate structures. For category A, domestic buildings, offices, and things like that, the psi factors of the psi factors are 0.7, 0.5, and 0.3. Now, if you look at the loads, and you see that's a foundation, that's the basement, that's level 0, you have a window or a door, and that's the side of a house. You see, this is the living room. Well, in a living room, the load, the mobile load in a living room, the characteristic value is 2 kilonewton per square meter. If the basement, for instance, is an office, then the characteristic load of the mobile load is 3 kilonewton per square meter. You take the stairs, and for staircases, it's 3 kilonewton per square meter, the mobile load. You come to the balcony, and in the balcony, it is 4 kilonewton per square meter. And from the balcony, you look at the stadium, and in a stadium, you will have 5 kilonewton per square meter. I make this silly drawing to help you remember this. If you know those figures, you can very easily determine all the loads in a building. It's always the same. Living room 2, office 3, staircases 3, balcony 4, stadium 5. Just remember that for a living room or a bedroom, it's the same. 2 kilonewton per square meter, it's not that much. It means it's only half a meter of paper. So if you are a student, be careful. If you put on the floor on your room half a meter of paper, that's the design value of the floor. Don't exaggerate in that. For those who have a waterbed, think about it. 20 centimeters is already 2 kilonewton per square meter. And most waterbeds have 30 centimeters of water in it. So it's far exceeding the design value of the mobile load of your bedroom. Now we will give you some values of mobile loads for different categories. For category A, we have seen it now, it's floors 2, stairs 3, and balconies 4. Office areas, it's 3, and that's for category B. And then you have category C. There are different subcategory C's, and category C is an area where people may congregate. So where there are tables, then it's 3 kilonewton per square meter. When there are fixed seats, it's 4. When there are no obstacles at all, it's 5. When there is a physical activities like dancing or something else like that, it's 5. And large crowds, it's also 5. This table comes from Eurocode 1. Then we arrive at category D, the shopping areas. When it's a general retail, a small shop, it is 5. A department store, it's also 5. And storage and industrial use, then if you have an accumulation of goods, it's 7.5. When it's for industrial use, it's 5. And then we have other categories, F, for instance, for a parking, traffic in a parking and in buildings, not traffic for bridges. That's something completely different. Only for traffic and a parking in a building where the cars are less than 30 kilonewton, then it's 2.5 kilonewton per square meter. So you see that the mobile load of a parking is less than the mobile load of an office. So you can turn an office into a parking, but you cannot turn a parking into an office. That's sometimes difficult to grasp. The category G is then for traffic and parking in buildings with a load, a vehicle load more than 30 kilonewton, so that's 5 kilonewton per square meter. Non-accessible roofs, it's 0.8 kilonewton per square meter. And accessible roofs, well, when they are accessible, it depends on the category A to G, because you can have a roof that is used as a parking, or you can have a roof that is used as a storage, and so on. And then the last category is special services like helicopters and things like that. Well, that has to be decided for what kind of helicopter can land on the roof, yes or no. This lecture taught us something about loads and their partial safety factors. And before installing a waterbed, think twice, because the maximum allowable load on your bedroom floor is only 200 kilograms per square meter, representing only 20 centimeters of water. See you at next lecture.